Okay. Hi, I'm Wenshan Wang. It's my pleasure to introduce Katerina Fragkiadaki. Katerina is an assistant professor in the machine learning department in CMU. She received her PhD from University of Pennsylvania in 2013 and was a postdoc in UC Berkeley and Google Research between 2013 and 2016. She has done significant research on video segmentation, motion dynamics learning, and on the area of projecting geometry into deep visual learning. Katerina's group develops algorithms for mobile computer vision and learning of physics and common sense by watching and interacting with the world. She received a Best PhD Thesis Award in 2013 and served as the area chair in CVPR, ICML, ICLR. Very recently, she got the NSF Career Award from NSF-IIS. She is an author of the SFMNet, Learning the Structure and Motion from Video in 2017, which has drawn a lot of attention and have many follow-up works since then. She pioneers the work of GRNN, Geometry-Aware Recurrent Neural Networks, in 2018. I have the privilege of working with Katerina in a recent project. I remember last week during the discussion, which is quite impressive. She asked her students to focus on the problems that are really going to make the difference and focus on the research that really makes things work in real life instead of doing incremental research or just improving the implementation. So I think that's quite remarkable. We can also see the same rationale behind her published works. So I'm looking forward to the talk. Let's welcome Katerina Fragkiadaki.
Wenshan, thank you for your kind intro. Shall I try to share my slides, my screen?
Sure.
Okay. Well, I'm supposed to be sharing now, right?
Yeah, we can see that.
I see. Okay. Thank you. That's very sweet. Thank you for your invitation and your introduction. So today, what I'm going to talk about will be less of how do we get learning-based SLAM, although I'll show you how we try to do our learning-based ego motion estimation. But mostly, what can you do if you have such ego stabilization? How can this help visual learning and visual understanding? Okay, and I'm very sorry that, you know, it's very bright, the screen. I'm not sure how to fix that one. So here is a baby, and we put a camera in its head, and the baby moves around. Actually, it must be a 1+ year old because it can, you know, walk quite reliably. It didn't fall throughout the video. And this is actually the data that we get. And as you see, there is a lot of zoom in, zoom out, tons of viewpoint variability, lots of occlusions. And it's hard to parse this type of videos with CNNs. It's hard to parse. Why it's hard to parse? What is the problem with convolutional neural nets of passing every individual frame through a CNN? Well, first of all, there is no object permanence. CNNs process each image independently, right? And if the camera moves and an object falls outside of the field of view, then it's not represented anymore. Yeah, objects change size, both in the image as well as in the deep feature maps. Objects move with camera motion, and all those problems are due to the fact that the camera motion, the camera viewpoint is entangled with the appearance of the scene in those feature maps. And here is SLAM, which actually is pretty hard to beat, this Orber SLAM 2, V2. You take as input a scene, and here, despite the fact that, you know, there is a lot of camera motion and so on in the video, the output, you see this disentanglement. We have disentangled how the scene looks like. You see this point cloud map and how the camera moves, right? So now that this is good. And objects persist, like the teddy bear was in some frames, was out in some other frames, but in the map it's still there, right? So we have object permanence. This is great. This is some basic spatial common sense. But what is the problem with SLAM? Well, I wouldn't say that the problem is moving objects and so on. I mean, we can learn, eventually we can learn to discard those and so on. The problem is that a SLAM cannot imagine, unless you see a part of the 3D space, you cannot actually represent it in the map. Despite the fact that you may have seen many similar scenes, you cannot actually learn with experience. You still, at the next time that you go in the similar scene, still you need to go around to be able to capture the full 3D scene. And this is not how we humans do it, right? If I've been in many similar scenes, next time, even from a single view, I can imagine the full thing. So this talk is how can we use LAM, simultaneous localization and mapping techniques to help deep visual learning, and how can we use architectures that are such SLAM-enabled deep network architectures to actually learn visual representations without human supervision. So this is the geometry-aware recurrent nets that Yenshan mentioned that actually take multiple images as input. The images can be RGB or RGBD, right? And associated depth maps. And what they build as a hidden state is a 3D feature map, all right? Much similar to SLAM. So they try to build a 3D map of the scene, and in terms of this voxel grid, and every voxel is represented with a long feature vector, okay? And the two main innovations of GRNNs over previous either RNNs or LSTMs and so on is that the hidden state, the bottleneck of the network, is 3-dimensional, which makes this feature map, what I show here with colors, is 4D, okay, X, Y, Z, and the number of feature channels. So that's number one. And number two is the way they update the map over time. They actually compute ego motion, much like SLAM, and then they use the output of ego motion estimation to update the map in a way that I'm going to describe right now. So I'm going to discuss about a very simple video going around the toaster. Actually, yeah, I think it's a toaster. So here is a toaster image. So what we do is we first unproject, we shoot a long rays, RGB values, and populate some grid, okay? And this grid is super incomplete, right? Because it's just computed from a single view. So lots of holes in that grid. But then we pass it through some 3D CNN, 3-dimensional convolutional network, and we actually, whose job is to imagine, whose job is to paint the map. All right, so here's the map. And here's the next frame where the camera has moved, the scene hasn't moved, but the camera has moved. And again, we'll unproject. So this is a differentiable unprojection operation. And again, this gray is pretty incomplete, but we're going to densify it, and our CNN will become better and better by looking more and more scenes. It's going to become better and better at imagination, at painting the missing details. So here's what's going to happen. We are going to compute ego motion between the map from the first frame and the current frame, and we'll use the output of ego motion, which is a 3D rotation and translation, to actually rotate and translate the current map before we fuse it with the map of the previous frame. So this explicit feature transformation, which is just a parameter-free layer, right, that transforms features based on estimated ego motion using dense transformers, essentially make sure that information from the same 3D physical viewpoint, from 3D physical point, end up nearby the map, right? Because otherwise, the CNN, if the camera moves, and then the same thing moves in the pixel image, there's no way for the CNN to associate them with its small kernels. Of course, transformers would help you, right? So explicit attention would help you. But here, on top of everything, we also have the stable 3D model of the scene. Here's a new frame. We'll do exactly the same thing, estimate ego motion, update the map, and so on. So this is like, so this 3D feature map now is the bottleneck of the network. Is geometrically consistent because it was built to be geometrically consistent, okay? And we can learn this whole network end to end from our favorite end task. But before we do that, we want to show that, look, despite the fact that the corner of the toaster is moving in pixel space, after the explicit transformation with this stabilization of the feature, right, that uses the pose estimation and how camera moves, essentially the same point lands in the same place in our mental 3D feature map, in the hidden state of our network. All right, well, it's all over the place in the 2D, and here you can see it. Here is a 2D RNN or 2D conv-LSTM or GRU, what such a model would do. Well, unfortunately, there's no ego motion estimation during representation learning. So now the corner moves in the feature maps, the blue feature maps, and because the hidden state is updated convolutionally, this same corner lands all over the place in the hidden state. And now what dictates the hidden state is how the camera moves as opposed to how the scene looks like. All right. So things won't generalize across different camera motions. So what can you do on top of this geometrically consistent hidden state, which is like a map of SLAM, but it's like in painting, and I'll show you what it means by in painted. It's like completed as opposed to just what you see from the visible views of the current video. Well, our favorite task for computer vision is detection of objects, and you can do exactly the same thing here. You can do 3D object detection. And so how are you going to do that? Well, you're just going to feed a Mascar CNN type of output on top of the feature map. Everything is differentiable. You can train it end to end if you have 3D object boxes. All right. And the only difference with Mascar CNN that takes 2D images and spits out 2D bounding boxes. Here we're going to be feeding 3D feature maps as opposed to 2D feature maps, and we'll be spitting out 3D bounding boxes. So the anchors also are 3-dimensional and so on. But beyond that, there is no other difference. So what you've gained is that even if your camera moves, because the 3D feature map stays there and the things do not actually disappear, objects persist over time. The features persist, so the objects also persist over time. So those operations have essentially this geometry-aware recurrent nets building object permanence in the neural network. All right. Because despite the fact that things move in and out or get occluded in the 2D observation stream, they actually persist and they don't interfere with one another in the 3D feature map, in the latent 3D feature map. The most exciting thing, though, regarding those networks is that you can train them unsupervised without human annotations just by predicting views, predicting how things look like from different viewpoints. Okay, so this task is called view prediction. It's a famous task because people think that it's biologically plausible that the brain learns by predicting observations in different levels of abstraction. Okay. Yeah, so let's see how to do it. Of course, you can do view prediction without having a geometry-aware neural network. You can have a bunch of frames. You can even fit the ego motion of some form, like concatenate with the image, and essentially train your architecture to do exactly the same thing, predict views. In fact, that's going to be our baseline. But here we'll show how a 3D bottleneck, this architectural bias of putting a 3D-dimensional neural bottleneck as well as doing ego motion stabilization while updating that bottleneck actually will allow you to generalize dramatically better. All right. So how does view prediction work? At training time, you collect a bunch of views. You make the 3D feature map by passing through the GRNN. I give you a query camera viewpoint. Then you rotate the map to that camera viewpoint and you project. And again, everything is, you know, differentiable, and you decode into some RGB image. All right. And then you backpropagate the gradients. And as we said, this is a self-supervised task, so you can train it with as much data as you like. Okay. By the way, at training time, you can have multiple views. At test time, you can just feed a single view. That's totally okay. So now let's see what happens. Let's see some results. So these are the different input views that I feed to the network. These look pretty simulated scenes, but soon we're going to go to real scenes. Okay. I just feed 3 different viewpoints with the corresponding RGBs. There's no depth here. And I let the network imagine the full scene and I record the video. And here is the video is playing. And the cool thing is that you can compare the geometry-aware recurrent network with another, you know, neural architecture that does not have such a 3D, how to say, architectural bias. So there are some artifacts when the GIF is running multiple times. By the way, the same video is just iterated again and again and again. And you see that in the second 2 rows, you have scenes with more objects, and our model was never trained with scenes with more than 2 objects, and still it can generalize to scenes with more than 2 objects, while the other network that has never used a 3D neural bottleneck or any type of SLAM or geometry in its architectural biases, it cannot generalize. I mean, you feed it 4 objects and it still sees 2 objects. I think this is super important. How we can strongly generalize to novel scenes. And this all comes from the fact that space is represented in the bottleneck of the network in a nice way. Yeah, so this was a simulation. And the question is, how can view prediction help us learn visual representations outside of the toy simulation worlds? And the answer is that yes, view prediction can still help us, but because the visual world is very multimodal, we may want to change the cost function. Instead of regressing to RGB values, we will be predicting features, and instead of RGB regression, we will be doing contrastive feature prediction in the following way. So here comes again the architecture. We have frames 1, frame 2. We have unprojected them and make a 3D feature map of the scene that the images depict. Okay, so this is this colored cuboid. And here comes a query view. And again, we compute the features from that view and the corresponding map. And we estimate, the first thing we do is we estimate the relative pose of that view from our current map. And what we do is we orient our map and even project it to 2D with some 2D network similar to the one that we use for predicting images. But now, instead of predicting 3 channels, we predict, let's say, 64 channels or whatever we want the number of feature channels to be. And then the same query view, we feed it through what we call a bottom-up 2D CNN. And what we do is we put some voxel-wise or pixel-wise contrastive losses there. So we have two of those. One is in the 3D space and one is in the 2D space. Okay, so the idea is that the map that I have built, when oriented to the query viewpoint, it really better match voxel-wise the 3D map of that target view, either in the 3D space or when it projected to 2D, as opposed to any other voxel or every other pixel feature vector. And you know, the same tricks hold here for any type of contrastive learning. It's good to have a big sampling of negatives. You can use dictionaries, like recent papers suggest, outside of the current batch, if you want to sample more negatives and so on. And these are all helpful to help learn good features. And that's it. All these weights in this slide are learned end-to-end. Nothing is initialized. They're trained from scratch. And what you do is so I'm just visualizing now the 3D feature map from overhead, because you can visualize, you can project that map and visualize whatever you like. So here's how things look like. I mean, you can kind of track the cars and so on. And indeed, we have some follow-up work that we show that, yeah, you can, these features are useful for 3D tracking. You can initialize a box and track it just following those features and just doing cross correlations of those features discovered from view prediction. So no annotations ever. And another test we did with those features is we use it as pre-training for 3D object detectors, the same task that I described earlier. And what we saw is that, yeah, it helps. And view contrastive prediction helps more than view regression, okay, of better pre-training, let's say, for 3D object detectors. But what else can we do with those architectures? We know that people can detect and segment objects in 3D without ever using any mask or 3D box, okay? They can detect and track without any supervision. So can we similarly discover objects without any annotations? So some things that we've tried to do with those architectures is the following. We take 2 frames and we stabilize them based on ego motion. And once we stabilize them, then we compute motion between those feature maps. And for this particular scene, which is a static scene, once you compute motion after stabilization, all these motion fields should be 0, because the camera motion has been factored out already, okay? So here is a dynamic scene. So far in the talk, we've only been looking at static scenes, like without independently moving objects. And here is how the map looks like if you superimpose 2 different feature maps before, stabilize them with ego motion estimation. And here is on the right is how it looks when it's stabilized. And you see when things are stabilized, the moving objects pop up. Unfortunately, other things also pop up because the features are not like perfectly slow. And in fact, this is the ongoing work. What is the golden architecture that can learn imagination of visual features beyond occlusions from single views that, you know, can generate slow features and so on and so forth. So we've been working on that front. But even with this kind of extremely naive 3D CNN architecture, still you see that, you know, the moving objects pop up. And then you can discover those flows. Like any optical flow in that 3D space that is non-zero signifies a moving object. And recently we even went beyond that, and we use larger time horizons to discover objects without any supervision in 3D. So this is discovery of objects in 3D, not in 2D, because of course all traditional video segmentation literature can segment objects in 2D, okay, by clustering point trajectories or something like that. And we've compared with using depth maps and ego motion, and because our model can in paint, can imagine, can actually predict the full extent of objects as opposed to only what's visible from the current view. All right, so we have endowed our architecture with the ability to imagine. So another thing you can do with those architectures is, can we organize our visual world into prototypes? All right. There is this dream of building a knowledge base, a visual knowledge base, so that we can parse any new image in terms of that visual knowledge base. And the question is, what is the right representation from that visual knowledge base? What should be our visual prototypes over which we'll be parsing our images? And yeah, so I would argue that 3D is a good representation. Look at all these crazy variations. There is a lot of different visual variations, but it's all the same 3D objects. So if you, represent your prototypes in terms of 3D feature maps, right? There is all the variability depending on pose and scale and motion. You can factor it out during matching with the architectures that we just discussed. These are some data sets that we have used. Look at this nice replica data set. Is simulation, but it looks very, like the real world. And what you see is things that look very similar in 3D. Once you project them from camera viewpoints, they look actually very dissimilar. All right. So that's it. So then if you want to discover concepts without annotations, without anybody telling you that actually this sofa is similar to that other sofa, all right, or this sofa with that, green pillow on top of it is not a sofa, it's actually a chair, like an armchair or something, is very similar to that other armchair with a white pillow. And if nobody wants to give you this annotation, then, well, maybe it's worth going into a 3D feature space, because in 3D feature space, the same objects, if you look at their feature context and you scale them and you search over the rotations, then you may really manage to get them to match. While in 2D projections, they actually look very different. If you project the chair from different viewpoints, it actually looks pretty dissimilar, right? So the important thing here, so here I'm showing the output of our system. And what this system does is it spits out 3D bounding boxes. And then it says C33. This means prototype 33, cluster 33. And then dash R40. This is the rotation. So basically, you discover sometimes of prototypes, and those prototypes are also represented in terms of 3D feature maps, okay, X, Y, Z, and number of channels. And then, concurrently, you are learning a 3D object detector, which is initialized from, a state-of-the-art 2D objectness detector where you kind of triangulate different detections from different viewpoints. So you iterate between detection, clustering, prototype learning, and then detection, again, clustering, prototype learning, and you kind of improve the detection over time. And essentially what you land at the end is a set of prototypes like those. Here we show the banana and the grape and the lemon and apple and so on. And then the images are parsed with respect to those prototypes by indicating which prototype it is, for example, cluster 10 or cluster 6 and so on, and in which rotation, okay? And all the different poses of a particular object, let's say broccoli, and all different scales are all explained by the same prototype, okay? So if you go into parsing, it's much more helpful to have your prototypes and your templates in that 3D format, okay? So we did this in Carla and in the replica dataset and in some more simplified simulation environment and so on. But basically the hope is, yeah, you should be able to do this in any photorealistic scene. And yeah, we are using ego motion and depth, but we also use that in a real world scene where ego motion was actually given by some SLAM system and so on. And again, we parse in terms of clusters and rotations and so on. Yeah, and since this is a learning-based SLAM workshop, I just want to discuss our architecture for ego motion estimation. I mean, it seems that they're much, much better out there, but the idea of what we're doing so far is you have a map, and you have the current frame, you lift them into 3D feature maps, and essentially then your neural network looks exactly like an optical flow with all the tricks of state-of-the-art optical flow, like coarse to fine, cross correlations, and so on and so forth. But instead of predicting dense 2D motion field, it predicts a 3D rotation and translation. And the other thing that you can do is, despite the fact that the point cloud is not complete, our 3D feature maps are always complete. Okay. And if you want to see how the R ego motion and learning-based ego motion estimation is compared to a state-of-the-art ORB SLAM, let's say, well, it is not that great. Let me show you the numbers in the validation set of Kitty. Well, is 1.6, while ORB SLAM is 0.2. However, if you blow up the resolution with sparse convolutions, which we're going to do, and if you, so that's number one you can do. And if you also add a small motion CNN, exactly like optical flow V2, like the FlowNet version 2, where they have some neural network specialized for small motions, then you can drive that 1.6 lower. And I think the interesting is how you can play with the architecture and have dramatically different results. While I would say the traditional SLAM architecture is kind of plateaued. I mean, it's hard to improve upon them more. Yeah, of course, it would be fantastic to have a great ego motion estimation method that at the same time can also infer things from single view, simply because it has seen, scenes and objects, how things look like from different viewpoints. So I'm going to stop here. I'm just going to say that domain knowledge from simultaneous localization and mapping, a traditional geometry-aware SLAM, can inspire neural architectures that can help generalization of deep networks for visual parsing. And yeah, and then we talked about ego motion stable 3D neural representations that help inject spatial reasoning to deep nets. We talked about object permanence, can learn without supervision by view prediction and neural background subtraction, okay, and can help organize the visual world into a small number of prototypes by increasing compressibility thanks to the 3D nature of the, let's say, parsing element, the prototypes that can explain different poses and scales and so on. And that's the end. This is the papers that I talked about, and these are my students. And thank you very much again for inviting me.
Okay. Thank you so much, Katerina. Here's a couple of questions from our audience on YouTube. Just to read them. One from S.Y. Chen. He is asking, how do you determine the size of your 3D hidden features field of view?
How do we decide how big is the map, for example? Okay, yeah. So this map, when you have a moving car, right? That map naturally moves with the car. Okay, so the answer is the following: you just pick the biggest map that GPU memory fits, and the higher resolution, the better. And resolution is a huge problem, and we have worked with sparse voxel grids, and this definitely help. But the idea is that, whatever fits in the GPU memory, imagine we're using our batch sizes are 1 or 2 or something crazy small, because yeah, these feature maps are pretty big in memory if you don't do something smart like sparsification and so on. Now, your question would be, okay, why don't you always sparsify? Well, the thing is, when you do view prediction, right, you do not know ahead of time what will be occupied or not from the other view, okay? So that's one difficulty. Yeah, so this is what we do. We put whatever big, whatever the biggest possible map that fits in our memory. Also, I need to tell you, since we're estimating camera motion, we know exactly what the camera is looking at. We know if the camera is looking outside of the map so that we can move the map to the right. Okay, so this type of memory allocation and management happens all the time in the network. Yeah.
Okay, one follow-up question from mine is like how large exactly are you using for now? Like
how large is what? The 3D feature maps?
Right, like if you take, for example, on KT data sets, how large is the feature map with respect
Yeah, it's like
to
100 by 100, and the height is much smaller. It's like maybe 16 or 32. This is the spatial dimension, and the feature may be 128 or something.
In meters? Or what's the unit?
Oh, in meters.
Okay.
Okay, so I do not know. The student knows how big is a voxel. I think a voxel is maybe 0.25 meters or something like that. Now I need to tell you something else. When we track, for example, we want to track objects here, right? And unsupervised. We detect an object, and then we create another map that is object-centric and really launch also that particular object, okay? So the truth is the following. With this type of architectures, the zooming in, zooming out, the foveation, all the time looking at different parts of the map and blowing up the resolution there is absolutely necessary. I think even if we go away from, kind of extremely memory-consuming voxels and we go to point clouds and feature clouds and so on, still foveation and zooming in different parts of the scene based on what you want to do is still extremely, extremely important. In fact, we saw it, like our tracking results went dramatically better once we were zooming on the objects that we were tracking, okay?
Okay, cool. Here's another question. Instead of using 3D voxels as hidden feature, some other works use 3D mesh as hidden space based on PyTorch 3D. What do you think of these approaches?
3D meshes. Yeah, and these meshes, do they have features on their kind of nodes or not? That's the question. So I may not understand the question correctly, but if the understanding is, take an image and predict a 3D mesh, which is just an arrangement of many points with triangles and so on. So we did work on that before. For example, we're trying to recover 3D meshes of humans from videos. The problem with mesh is that it's very hard to be done if you don't have a low parametric model of that mesh. Okay, like you cannot just take a picture of my office, which is absolutely messy and has tons of different objects and has even, this type of paper towels and so on, that is very, very hard to figure out how to encode it in a mesh. While in the 3D feature map, you really don't worry. You just put the features there and you're saying, those features are going to capture that paper. Whatever is the feature is going to be trained end-to-end from the final task and so on and so forth. In fact, that's exactly our problem with the meshes, that you really need to specify the geometry and the topology and so on. Yeah.
Okay, great. Path, here's another question from Path. Prototypes are rigid, which seems a big problem, and doing a rotation check over all angles seems extremely computationally expensive. What do you think of the problem?
Right. Could you repeat the question louder, please?
Okay. Prototypes are rigid, which seems a big problem, and doing a rotation check over all angles seems extremely computationally expensive.
Sure.
What do you think of the problem?
Yeah, sure. I'll tell you what I think. So this is our very, very first step. It's absolutely a baby step. Rigid is bad. I'll tell you one progress we made, which is not a lot of progress, still rigid, but now we disentangle the object into content and style, and we only use prototypes of content or prototypes of style separately, and styles are 1D and contents are 4D, exactly like that. But absolutely, this is exactly what we're working on right now, how we can learn deformable prototypes, articulated part-based models to represent the objects. That's number one. Number two, this thing that you said with the rotation, that is true. It is extremely time-consuming. First of all, it can be parallelized. You don't need to search every view separately. What I would imagine is that if we want to do 3D parsing, we really need to couple it with a policy learning that says, oh, based on this, which object shall I search first? And when you search for objects, you forget about the 3D arrangement. You can pull across the space, make some 1D vector, pick up your top 100 categories, then search there more. But you will see many people saying that, yes, inferring the right pose is actually very, very time consuming. It's much easier to tell me that this is a pen and much harder to tell me if the pen is facing upwards or downwards. Even for humans, it takes much more time to infer pose than to infer the label of an object. Yeah, that's my answer. Okay. But this is an excellent question.
Okay, so is the 3D representation limited to a single object, or the motions have to be around the specific object to let the model to learn enough to build a reliable 3D representation?
yeah, I think the question is, do you put the objects in the middle of the scene? Maybe this is the question. No, you don't need to put the objects in the middle of the scene. The only reason to put the objects in the middle of the scene is resolution. If we had infinite resolution, we would put, you know, a homologous grid, then we'll run our detector, focus into objects if we like to zoom in and more and get high resolution prototypes and so on. No, it shouldn't. In fact, the whole point of this architecture is that you don't know where the objects are and you do this thing so that to infer where the objects are in the first place. In fact, the 3D detectors do very well on top of those representations because things in 3D do not interfere with one another and so on.
Is the example of identifying cars from 2D image in this example of identifying car from 2D image, how does the model learn the 3D representation of cars that are robust to changing of the background?
Great question. So how does it? Well, first of all, the first thing you do with this prototype thing that I mentioned is that you do view prediction. You go around tons of scenes, you do view prediction. So your network has learned to look at the backgrounds and so on of any type of different background. Now I can tell you some super recent thing that we've done, which is the following. These neural three, I'm very excited about, but it's just extremely recent, so it's not like super mature. You have those objects, and then you have the background scenes, right? And our networks essentially disentangle background scene from objects. Then you can take those feature maps, go in your favorite new background, for example, your new kitchen, build a 3D feature map because it's a static environment, and then paste, like imagine pasting objects and different lemons and so on against this new background, right? Because those representations are spatially disentangled. And then you can create new training data for you, and you can train your object detector on top of those compositions, right? Because these 3D new representations are compositional, you can mix and match and so on. And now your object detection, where you learn the lemon against the gray background or against the kitchen of your friend, now you can detect the lemon in your kitchen by this imagination, okay? By this imagination type of training data.
Right, yeah, that sounds really interesting. Maybe let's end with the last question. So in terms, because the SLAM, you have already shown that using SLAM can facilitate the object detection, can help learn this 3D representation. So I was wondering, how can we use this 3D representation in terms of navigation, not other tasks like localization and navigation? You have already shown some example of. Yes,
very nice. All right, so the other way around. So first of all, I think the works of Saurabh Gupta and Devendra Shaplot and right, so they do use their 3D. No, they don't use 3D feature maps. They use 2D feature maps of the ground floor because, you know, for navigation maybe it's not important the vertical dimension as it's important for manipulation or object detection and so on, right? And yeah, they do use those feature maps. They learn to paint, they learn how to move in those maps. So I would say, and actually Saurabh started with completely unconstrained feature maps. Like basically every point on the floor could save whatever 1D feature vector it wanted. But it seems that in a recent, actually CVPR 2020 paper, they just predict occupancy. They learn how to predict occupancy so that if you open your eyes from a single view, you can have a ground floor map of occupancy, right? Which is good. You don't need to go around to figure out if it's empty or not. So that's great. Now, how to do better ego stabilization? I'm pretty sure that eventually, you know, such a neural net will be able to spit out awesome ego motion. I think resolution is important. And the neural network architecture, I remember it also took quite a long time for optical flow to be learning based completely, right? From a flow net versus, you know, traditional method. And this had to do with the architecture. We had to specialize. In fact, it may have happened already, and that I'm not just aware. I do expect in this CVPR, or maybe even earlier, that already there is some neural net that spits out pretty awesome ego motion. I think it's a matter of architecture, searching the right architecture bias to do exactly that. Yeah. So we are working on this because ego motion estimation is crazy important for this work.
Okay. Thank you. There's more questions on the YouTube chat. So if you have time, you can like interact with them after the talk. Okay, thank you,
sure.
Katerina.
Yeah, you can send me an email with the questions. Absolutely, yeah. Right?
Okay, right. Thank you.
Thank you so much.